Good morning. Sorry, I have to find the passcode here to log in. Okay. Doing live. All right. So just as a reminder, the first homework is due today, and then the next one will be due a week from today. And you'll have to excuse me, I have a little cold, so my voice might be a little weak. All right, so I think in the last lecture, we did a little review of probability and statistics and linear algebra. So we're going to finish that momentarily and then talk about random processes, discrete and continuous random processes a little bit, and then start on the real material with Neyman-Pearson detection theory and so on. Okay. So just to kind of pick up where the last lecture ended, let's suppose that you are given the following problem. Actually, let me use this other paper. I think it might have better contrast. Okay, so suppose that you're given a random variable y. This is a vector with covariance of y. It's just c sub y. Okay? And what you would like to do is to choose a matrix A and a vector B in such a way that y equals ax plus b would give you a random variable A that would be having a covariance matrix that is identity. Okay? And so the idea here is, this is called basically whitening, which is you take a random variable that you have and you want to produce another random variable from it, which has a covariance matrix which is diagonal. Okay? So basically what you want to do is diagonalize this matrix CY. So let's say that we have, let's start with x. Suppose the expected value of x 0 and the covariance of x, just the covariance of x is c sub x. And from this, as you remember from last time, when you have this kind of expression, then the covariance of y is A times Cx times A transpose. Okay? So let's now choose Cx to be defined by V dV transpose. Okay, so this is a covariance matrix. It's symmetric, positive, definite. So I can write it as with an eigenvalue decomposition, which is V dV transpose. Okay. All right. So let's see what covariance of y would look like with this definition. So this would be A V D V transpose A transpose. Okay. So all I've done, I've taken this Cx, I've taken this eigen decomposition, and I've stuck it in the middle of here. Now I have the covariance of y is equal to this thing. Okay? All right, now, if I let A be equal to V transpose, let's see what happens. Then Cy becomes V transpose V D V transpose V. Right? And because this is symmetric, positive, definite, so this V and V transpose, they're both orthogonal matrices, which means V transpose V and V transpose V here are both identity. Okay? So this is identity, and this is identity, so this becomes a diagonal matrix. Okay? So what we've done is, by virtue of choosing this transformation to be the transpose of V, which contains the eigenvectors of Cx, we've managed to come up with a Cy, which is diagonal. And of course, the elements of this diagonal are simply the variances of the different elements of x. Okay? So this is basically what it's doing is it's taking a random variable x, which might have an arbitrary covariance matrix. In other words, the off-diagonal elements may not be 0, and turning it into a random variable y, which necessarily has off-diagonal elements in the covariance which are 0. And that means that the different elements in the vector y are now uncorrelated. And that's the whole idea behind whitening, is you take a random variable, a random vector which has correlated values in it, and you turn it into one that has uncorrelated values. Okay? Okay, so this is the general idea of whitening. Okay, now let's do kind of something slightly different. Now suppose you're given a random variable x, which is, let's say, Gaussian, with 0 mean, and identity covariance matrix. Now, first of all, in MATLAB, how do we generate something like this? This is very simple. Just say x. Let's say this I is 100 by 100. So that x is 100 by 1 vector. Okay? So the way you generate this in MATLAB is you just say x equals rand_n 100, comma 1. And this produces a vector like this, x1, x2, xn, where n is equal to 100. Okay? So this is how you do this in MATLAB. And what you want now, so this is easy to produce in MATLAB. What's a little bit more complicated to produce is you want the random variable y such that its expected value is, let's say, some value b, and its covariance is some matrix C. Okay? So this is easy to produce. How do I produce this now, given that I have this vector? Okay? So the way you do it is basically using, again, the similar kind of transformation. You say y equals ax plus b. Okay, so from this, obviously the expected value of y is equal to the expected value of ax, which is 0, plus b. So this is b, so this part is done. Okay? That was easy. On the other hand, covariance of y is A times covariance of x times A transpose. So this is A times identity times A transpose. So this is A transpose. Okay? Now what I want is I want A transpose to be equal to this C here. Okay, so how do we do this? We're at C equals A transpose. And now remember, you can write C because C is a symmetric positive definite matrix. You can write its eigendecomposition. That would be V D V transpose. Okay? And now I can break this D. D, remember, along the diagonal, it has the eigenvalues. Because C is symmetric positive definite, these eigenvalues are real and positive. Therefore, I can write down their square root. So I can write this matrix as V t to the 1/2 t to the 1/2 V transpose. Okay? Now these two are again diagonal, so I can write this as V d to the 1/2 then d to the 1/2 transpose V transpose. I can just put the transpose there because the transpose is going to make no difference since this is a diagonal matrix. Okay? So now you think of these two, this and this. You define this as A. Okay? And then this becomes A transpose. Now you can see how you're going to get the A that you need. So if you take your matrix C that you're given, write its eigendecomposition, and then take the square root of the eigenvalues and compute V times d to the 1/2. That is the A you need to multiply by this X so that you would get the covariance matrix that you're looking for. Okay? So this whole description here is to allow you to simulate a random variable with a desired expected value and covariance from one where the expected value of covariance is fixed because of the way that MATLAB generates things. Okay, is this clear? Any questions? So the steps would be, you do this in MATLAB, then you say y equals ax plus b with a defined this way. By the way, another way to find this A in MATLAB is you can use a function called SQRTM of C. This is called the matrix square root. This is not the same thing as SQRT of an argument. This is the matrix square root, which is defined like this. If you just say SQRT of a matrix, then what that does is it computes the square root of each element of the matrix. That is not the same thing as the matrix square root. Okay? It's not the element-wise square root. All right. Okay, now let's go on to random processes. Okay, a random process is nothing but a sequence, possibly infinite sequence, of random variables that are somehow related to each other in one way or another. Okay, what we are going to be interested in this class are mostly discrete random variables. Okay, so what we have is a sequence of numbers indexed by the integers n. Are you taking notes with that?
I'm just popping up MATLAB.
Could you put it away? We're not going to be using MATLAB in the course. I'd rather have you concentrate on this stuff. Okay, so n is the positive integers. So this basically is x of 0, x of 1, and so on. X of n, and it may in fact go off to, infinity, maybe infinitely long. So each one of these xn's is a random variable, and as I said, they're somehow related to each other. More specifically, what we're going to be interested in are so-called wide-sense stationary random processes. What defines a wide-sense stationary random process? Well, there's two things, two properties. One is that the expected value of x of n is a constant value. As I said, each one of the x of n's on its own is a random variable, and therefore, on its own, it can have some expected value. So what's special about these wide-sense stationary processes, one thing that's special about them, is the average value, the expected value at any given point in time, n, is the same. Okay, so this m could be changing, but it's not. Okay, so this is constant mean. Okay, the second property is that the expected value of x of n times x of n plus k is equal to some r of k, which what this means that is depends on the lag k only. So what this is looking for is basically looking at the correlation or the covariance between a value at time n and a value at time n plus k. And what this is saying is that the correlation or the covariance between these two only depends on how far away the two samples are. So for instance, the expected value of x of 1 times x of 11 would be the same as the expected value of x of 10 and x of 21. So because they're both 10 spaces away, as long as that space is preserved, it doesn't matter where the two samples occur, the covariance between them is always the same, and only a function of the separation between the two samples in time.
Wait, how is this different from a cyclostationary process?
Pardon me?
How is this different from a cyclostationary
The
process?
cyclostationary process, this thing actually repeats over time, and the mean repeats over time as well. In other words, it's not fixed, but it changes and it stops and it changes again in a cyclic way. Okay? These things are a different class of functions. Okay, so this guy here is called the correlation function, and we'll say more about it later. So these two are the defining properties of the White-sense stationary random processes. And these are the types of things that we're going to be dealing with for the most part. Okay. So for these White-sense stationary processes, we define various characteristic functions, one of them being the autocovariance function. The autocovariance function is defined like this, right? Cxx as a function of k. This is the expected value of x of n minus m. And this m is the constant mean that we talked about, times x of n plus k minus m. Okay? So this is very similar to what you saw up here, except for the fact that here the mean is not subtracted from x of n. Here the mean is subtracted from x of n. Okay? So if we write this out, multiply it through and take expected values and so on and so forth, this becomes the expected value x of n plus k minus m squared. This is after a couple of steps of algebra. Okay? And therefore, this is just r of k minus m squared. Sometimes we also put xx here to denote that this is the correlation function between a value of x and another value of x from the same process. Okay, so this thing is what I defined up here, which was, this is the autocorrelation function, and this is the autocovariance function down here. The only difference between them is mean is not subtracted, mean is subtracted. Okay, just like we computed the covariance between a random variable xn and another random variable xn plus k, we may in fact have two different random processes, and we can compute covariances between them as well. That's just a generalization of the concept that I just showed you here. So now suppose you have two random processes, x of n and y of n. Now you might think, well, what is, what's an example of these, say two random processes like this? For example, the first one could be the temperature in this room at different days of the week. Okay? The second one could be the number of people in this room during different days of the week. And you might think somehow these two things are correlated, right? I mean, if the temperature setting is not changing, but on some days there's more people in this room, then the temperature would be higher, right? People generate heat. So the numbers in this sequence and the numbers in this sequence are going to be somehow correlated. Okay, exactly how? We can define that by using so-called cross-correlation or cross-covariance functions. So the cross-correlation function is defined as follows, very similar to before. Instead of rxx, now we're going to write rxy. Rxy of k, and these are both White-sense stationary, we're going to assume. This is going to be the expected value of x of n, y of n plus k. So the second one is not x anymore, it's y. It's the other random variable. So this is called the cross correlation function. Okay? Now, we can also write it this way. Ryx, okay, this would be expected value of y of n, x of n plus k. It is important to remember that these two things are not the same. This is not equal to rxy, okay. Okay, these two are not the same. They certainly share many properties, and we'll talk about that very soon, but they're generally not the same. And of course, related to this is also the autocovariance or the cross covariance function. The cross covariance function is Cxy, just Rxy of k, minus Mx My. And I'm assuming that Mx and My are the means of this random process and this other random process. Okay, so now there's a lot of properties that these things satisfy, which we need to discuss. Okay, so first of all, let's think about this. Rxx at 0. What is the autocorrelation function at a lag of 0? Well, this is expected value of x of n times x of n plus 0, right? So this is the expected value of x squared of n, which means that it always has to be positive. Okay? So in other words, if you make a plot of this function, at 0, it has to be positive. Another property, Rxx of k, remember this is an expected value x of n plus k. Okay? And let's rewrite this. Let's make a change of variables. Let's call it n plus k. Let's call it m. Okay? We're just doing a change of variables. Then this becomes the expected value x of m minus k, x of m. Okay? Now if you look at this, this is simply a different way of writing the same thing. This is just Rxx of minus k. Okay? So if you look at these two, what that shows you is that the autocorrelation function has to be symmetric. In other words, if I wanted to make a plot, say this is k, and this is 0, I wanted to plot Rxk for any random process, it would probably look something like this. Okay? I mean, whatever shape this side has, the other side must have exactly the same shape. Sorry, you can't see all the way down at the bottom of that. Okay. Now let's do some examples. Let me draw a couple of these and see if we can think about what they mean. So let me draw this one. So this is k. So this is some value q, let's say, and everywhere else it's 0. Okay, so I'm just saying this is Rxx k. This is k equals 0. Okay? So what does this mean? This means Rxx k, which is expected value x of n plus k, is some q times delta of k, right? That's just another way to write it. This delta function is 1 at 0 and it's 0 everywhere else. So what does it mean? It means that all the values of x are uncorrelated with each other. Right? That is the definition of white noise. Okay, so you saw earlier we had a sequence of numbers in a vector, and we computed a covariance matrix from it, which was whitened. In other words, off-diagonal elements were 0. What that meant was that each of the elements of that vector were uncorrelated. This is just an infinite version of the same thing. So this corresponds to white noise. Now, it's not necessarily Gaussian, but it's white. And what is the variance of xn in this case? It's just q. Okay? Because this would be, if we assume that expected value of xn is equal to 0, then this would be just a variance. So this is one type of autocorrelation function. The more typical is the one that I drew before, where you have some function that starts at a large positive value, and then it decays as you go far away. What that means, so this function here that I drew for you, if this is kind of decaying as you go away from 0, what it means is that samples of x that are near each other are highly correlated. Samples of x that are far away from each other become more and more uncorrelated. That's pretty typical. Okay? Okay, one way to characterize the autocorrelation function is to look at it in the frequency domain. And in order to do that, we look at the discrete time Fourier transform. This is just a reminder that if you have a sequence, any sequence, let's say R of n, then the Fourier transform R of f of this would be the sum R of n e to the minus 2 pi j fn, where n equals minus infinity to infinity. So this is just a definition of the discrete time Fourier transform for any sequence R of n. Now we're going to apply this to the autocorrelation function. So R to Rxx of k. And we define it like this. We write P sub xx of f is equal to the sum k is minus infinity to infinity Rxx k e to the minus 2 pi j fk. Okay, this is the frequency, of course. This is the autocorrelation function. And this function here, this Pxx, is called the power spectrum. Or sometimes it's called the power spectral density. But why do we do this? Well, there's several reasons to do this. One of them is that the matrix, the function Rxxk, remember it's symmetric. It's real, it's symmetric. And therefore, the discrete time Fourier transform tells you a lot about it. The discrete time Fourier transform is a very useful tool to extract information about the periodic properties of these types of functions. So this is something we use very often. So let's take a look at one of these things. So for instance, let's take the example that we just had before. Let's say Rxx of k is sigma squared times this delta function that we just wrote down before. Okay, right here I write sigma squared before I wrote q. And this is the delta function. Okay, so if you take this and you plug it into this expression, what you get is the power spectrum is sigma squared for all f. So the power spectrum as a function of frequency would look like that. And this this height here would be sigma squared. Okay, so remember this corresponded to white noise. So the power spectrum of white noise is a constant value, where that constant value is the variance of the random process. This tells you kind of why this is called white noise. Yeah.
Can you disable the autofocus?
Pardon me?
Can you disable the autofocus?
Oh, is it kind of going crazy again?
Yeah.
Oh, you know, I don't know how to disable the auto. Oh, here we go. Okay, yeah, that's better. Okay. So this, as I was saying, tells you why it's called white noise. The white refers to a very old idea of looking at light through a prism, right? So when light goes through, the white light goes through prism, it gives you what? It gives you all the different colors of the rainbow, right? So what that means is that white light, pure white light, has all the colors of the spectrum in it at equal power. Okay? So white noise has all the frequencies of the noise in it at equal power sigma squared. That's why it's called white noise. Okay? So now this doesn't say anything about the actual distribution of the noise. It just says that the signal or this particular random process has the same power at every frequency. Okay, so then the real reason why we look at these things is we want to understand how noise behaves when it is put through a linear system. Now the linear system descriptions, these are the old things that you've seen before. So let's do a quick description of these things. Linear shift invariant system. So you have a signal x of n. So in our case, it's going to be a random process. And you've got a linear shift invariant system here, which produces another random process, y of n. Okay, you know well that y of n is x of n convolved with h of n. Okay, where this h of n is called the impulse response. Okay, and of course the equation that defines this is h of m x of n minus m. M is minus infinity to infinity. This is just the convolution equation. Okay? If you take h of n to the discrete time Fourier transform domain, you get some function h of f, where this f is frequency. This is going to be called the frequency response. Okay, and this is simply this h of f. It has a formula, which is the formula that you saw before. It's just a Fourier transform of this h of n. Okay, so what are we going to do with this now? Okay. Also want to remember that convolution is multiplication. Okay, in the frequency domain. So now what I want to do is ask, if I take this input to be a random process, and let's say this guy has autocorrelation function Rxx, okay. This guy is going to have autocorrelation function Ryy, okay. How are these two related? Let me give you an example. Suppose that I take this x of n to be white noise. So the elements of x are completely uncorrelated with each other. All right? Just a bunch of random numbers, uncorrelated. I feed them into this linear system. What does the linear system do? The linear system performs a convolution. Okay? Let's take a look at this. It performs the same thing, right? So the output of the linear system at any given point in time is a linear combination of the inputs, right? By definition. So, would you expect the output to also be white? No, right? The elements of the input are not correlated, but the elements of the output are linear combinations of the elements of the input. Therefore, they're going to be related to each other. Therefore, you can't expect this guy to describe a white noise process anymore. So here's what happens. So RYY, okay, so the definition of this, of course, is expected value of y of n plus k. Now I'm not going to go through the algebra for this. This turns out to be equal to h of k convolved with h of minus k convolved with rxx. Okay. Okay. So the impulse response plays a role. The impulse response gets convolved with rxx. But here's the tricky thing. Because this guy has to be symmetric, you cannot expect RYY to just be the impulse response convolved with RXX, because H is not necessarily symmetric, right? And therefore this other term shows up here to make sure everything is symmetric. Okay? So again, using the Fourier transform, Pyy of f is h of f, h star f. So you just take Fourier transform of this. The Fourier transform of h is h of f. The Fourier transform or time reverse version is the complex conjugate times pxx of f. Now, of course, you multiply h with its complex conjugate, you get magnitude h of f squared times pxx of f. Okay? All right, in other words, so for example, if the input was white noise, this guy here, pxx, would be flat, right? Now suppose that h of n is a low-pass filter. If it was a low-pass filter, then its magnitude squared frequency response would be something that would decay at some point, right? So now you're multiplying these two together, and therefore the output is going to look like something that has some values at the low frequencies, and it's going to die out at the high frequencies. It's no longer going to be white noise. So just to graphically show you, so this guy might be, you know, a constant as a function of f. This guy might times. This guy might look, let's see, it might look something like this. If you multiply these point by point, this guy is going to look something like that. So its spectrum is not going to be flattening. Okay. Any questions about this? Okay, similar kinds of relationships we can write down with respect to the cross correlation. So let's write down Rxy of k. So remember, this is expected value x of n, y of n plus k. And Ryx, okay, it's just the negative. Rxy minus k. Okay. So now I'm going to suppose that y and x are not just two arbitrary random processes, but one is the output and one is the input of a linear shift-to-variance system. So now, what can I say about these things, more generally speaking? Well, Rxy of k is h of k convolved with Rxx. Okay. So in other words, the input autocorrelation function convolved with the points, convolved with the impulse response, gives you the cross-correlation function between the input and the output. And correspondingly, Ryx of k is h of minus k convolved with Rxx of k. Now, strictly speaking, I could have put minus k here as well. Okay? But Rxx of minus k is the same thing as Rxx of k, so it doesn't really matter. So this is the only part that changes. And again, using the Fourier transform, what we have is Pxy of f. So these are the cross power spectrum. These are called the cross power spectrum. This is h of f, Pxx of f, and correspondingly Pyx of f. H star of f, Pxx. Okay, so why are these things useful? One of the reasons is something called system identification. Okay, this is a very broad topic. There's a lot that has been written on it. And the idea is the following. You have a system like this. You don't know what's inside this box. It's a black box. All you can do is give it an input and measure the output. Okay? And what you want to do is figure out what's going on inside that box. Another word for system identification is reverse engineering. Okay? You get a circuit that some other company built. You want to see what it's doing inside. You give it different inputs, and you watch the outputs, and you try to reconstruct the circuitry inside. Here's a very simple version of that. You have this, you give it some inputs, and you measure the outputs, and you want to figure out what H of N is. So let's see what happens. So just write down a very, very simple description of this. Okay, so here's the input. Let's look at it in the frequency domain. Here's the output. Okay, let's look at the cross power spectra. Pxy of f is equal to h of f, Pxx of f. Okay, so what you can do is you can give the system your whatever input you want and measure the corresponding output. And then you're going to ask yourself the question, what is this h of f? One way to do it is h of f could be Pxy of f divided by Pxx of f, right? So you could do this, you measure this guy, and then divide them. And then say, okay, well, that's my h of f. Do an inverse Fourier transform and get h of n and declare victory, right? Anybody see a problem with this? None of you see a problem with it? When you divide by something, what do you have to worry about?
Zero.
Zero, right? So, if you choose an arbitrary input to put in here, you have to worry about this denominator getting really small at some point. So for instance, what would be a good thing to put in to make sure that the denominator never gets small? We just talked about it. What is the one power spectrum that I described to you earlier that never goes to zero? White noise, right? So that would be a good example of where white noise is useful. If you use white noise, then this denominator stays at a constant, never hits zero. You don't have to worry about it. All you have to measure is the cross power spectrum between the input and the output. Do the inverse Fourier transform, and you've done system identification. Now, this will work if you have, in fact, a linear time invariant system. Right? Most of the time, when you have a really complicated piece of circuitry that you're trying to reverse engineer, it is neither linear nor time invariant. Okay? This will work for very simple things, like little pieces of that system. But if you have a nonlinear element in your circuitry, which oftentimes you do, then this would not work. But it is a very interesting example of seeing where white noise is really the only thing that is going to give you all the information you want. Right? I mean, you wouldn't think of using white noise. You would think of using some clever signal to put into that input so you can measure some clever output. You can do that too. Well, white noise does everything because it excites the system with every frequency possible. And so you're measuring the output everywhere across the frequency level. Okay, so this is kind of some review concepts on random processes.
This is pretty much the same as just pinging the system with a delta and just taking h of n just from the output.
No, it is not the same thing as pinging the system with a delta, because the delta here is not the signal. The delta here is the autocorrelation function of the signal. So what you're hitting the system with here is a sequence of random numbers that are uncorrelated with each other. That's called white noise.
Right, but say if you just provide the system with a delta, what you will measure on the output will be the impulse response.
Right, so that's right. So one way to do that would be to hit the system with a delta and measure the output. I'm just trying to motivate here the use of the random process component of things. Okay. Okay, so what I'm going to start doing now is begin to discuss statistical decision theory. And so this is the material that, I guess in all fairness, really is the new material starting now. Okay. Okay, so as we described a little bit earlier in the last couple of lectures, the first sort of canonical problem that we're going to discuss is going to be the simple binary hypothesis test. So there's two situations, H0 and H1. This is what we call the null hypothesis, and this is what we call the alternate hypothesis. And the idea here is to simply, given the data, try to tell which one of these hypotheses is the valid one. And there's different situations under which we're going to study this particular problem. So, two main scenarios. The first one is what we call the situation where you have no prior information. I'll explain what that means in a moment. And this leads us to the so-called Neyman-Pearson detectors. The second one is when we have prior information. Okay, so no prior information means the following. It means in these two situations, H0 and H1, we have no idea ahead of time which one of them is the more likely scenario. Okay? Because I could tell you, suppose this one would be, H0 would be, it's going to rain tomorrow. H1 would be, it's not going to rain tomorrow. Suppose I had no other, I just landed from outer space. I have no prior information as to what time of the year it is, how often it rains on Earth, whatever. So I don't know which one of these to think is more likely. Okay, so that's this first setup. The second one is where you have prior information. For example, you might say ahead of time, even before you collected any data at all, the probability that H0 will happen is, let's say, some little p, and the probability that H1 will happen is 1 minus p. And this leads us to the scenario called Bayes' risk. Okay, which comes a little bit later. The first sort of most directly useful stuff that we're going to do is these Neyman-Pearson detectors. Okay, so let's start with a simple example. Suppose you have two data points, or sorry, one data point, two scenarios. H0, you have some data point x, just a single number, right? Not even multiple measurements, just a single number. This guy is distributed as a Gaussian with a zero mean and unit variance. And under this other scenario, x is distributed again as a Gaussian, but the mean is different this time. It's 1, and the variance is still the same thing, 1, 1. Okay? So let's draw the picture for this situation. Okay, so this is the first one. It's 0. The second one is supposed to look exactly the same to within, my imperfect drawing, and that's 1. Okay, so this is in this density, and this is in this density. Okay? So, what I've drawn are the probability densities, P of x given H0, and I've also drawn, that's this guy, I've also drawn P of x given H1. Okay? This is the probability density for x given H0. This is the probability density for x given H1. All right, now I look at the value of x and I choose. I choose H0 and I choose H1, or I choose H1. How many different kinds of mistakes can I make? Well, I could choose H0 when H1 was true, or I could choose H1 when H0 was true, right? So two different types of errors. So two different error types. First one, you decide H0 when H1 is true. And how likely is it for that to happen? Well, I can measure what's the probability that x is less than some threshold gamma given H1. And the second one is you decide H1 when H0 is true. And this is the probability that x is bigger than gamma given H0. Okay, so let's look at these for a second. Implicit in the description that I just gave you is that you're going to make your decision by comparing the value of x that you measured to some threshold. So if you look at these distributions, and I make a measurement, I reach into a bag and I pull out a value of x, then I look at this distribution. If that value of x is near this bump, then I would pick H0. If the value of x is near this bump, I pick H1. So in other words, somehow I pick a threshold, let's call it gamma. And if x is less than that gamma, I pick 1. If x is bigger than gamma, I pick the other. Make sense? All right. And now I want to look at which one of these two, I want to look at these two probabilities of error and see how these two things are affected based on how I choose my threshold. Okay, so let's take a look at what these probabilities look like in this picture. First, let's look at this one. What is the probability that x is less than gamma given H1? Okay, so I'm going to color this one red. Okay, when you say given H1, it means I'm going to be working with the distribution for H1. So I go to this curve. Okay? Probability that x is less than gamma. Let's say I pick my threshold to be here. Okay? Okay, so now I look at the probability that x is less than gamma. So I draw this line, and this is my gamma. What is the probability that x is less than gamma? Probability that x is less than gamma is the area under this curve to the left of gamma. Right? Anybody not agree with that? Okay. So that's this guy. All right, on the other hand, this probability here, let's do it in blue. Probability that x is bigger than gamma given H0. So you go to this curve because it's H0, and you look at the probability of x bigger than gamma. That's this area here. Okay? What do you see from this? What you observe is that depending on how you choose your gamma, you trade off these two types of errors. In other words, you can never make them both 0. You can never, ever make a perfect decision. Because if you move this gamma to the right, the red area, which is the error 1, would get bigger. The other one gets smaller. If you move gamma to the left, the opposite happens. Right? The moral of the story here is that the whole game here is to pick a threshold gamma that somehow compromises between this type of error and this type of error. Given that you can never make the perfect decision, you have to somehow decide how this gamma is going to be selected. Now, in general, when you don't have a prior information about which one of these two hypotheses is more likely, what you do is you study the performance of this decision-making process as a function of all the values gamma. You plot it kind of as a function of all the values gamma. And then you decide based on that what gamma suits your needs best. Okay? On the other hand, if I told you it was twice as likely for H1 to be true than H0, then somehow I've told you how to set that threshold. Okay? And that's the Bayesian approach, which we'll get to after we finish discussing the Lehman-Pearson formulation. Okay? So the main message here is that you're trading off the value of the threshold for different types of error. All right, so let's write this down. So here are the salient points. Changing gamma will trade off one type of error for another. This is what I just said. Okay, so now let's make some definitions. The probability that x is bigger than gamma, given h0, is called the false alarm rate. And we denote it by the PF or PFA. Why is it called a false alarm? Well, you're saying x is bigger than gamma, you're saying something is happening. You're saying H1 is true, when in fact nothing is true. Right? H1 is not true. That's why it's called a false alarm rate. It's just a definition. On the other hand, the probability that x is less than gamma, given H1, this one is called missed detection rate, called P sub m. Why is it missed detection? Because H1 was true. However, your threshold was set such that you didn't catch it. So we call it missed detection. Now, of course, related to this, we can write PM as 1 minus the probability that x is bigger than gamma, given H1. Okay, remember this is x less than gamma. You can write it as 1 minus probability that x is bigger than gamma, given H1. Why do I bother with this? Because this is the quantity that I more often will be working with. And this is called, we call this P sub d, and it's called the detection probability. Okay? Now, in order to quantify the performance of a detection or decision system, we look at the pair of numbers, PF and PD. And remember, both of these are a function of your threshold. Okay? So this pair of numbers characterizes the performance of whatever decision-making algorithm you've chosen. The one that I chose here was just pick a threshold and see if it's big or small. But these quantities will always characterize the performance of whatever decision-making process you choose. Okay, so this pair of numbers is often plotted to give you a graphical description of how a particular system for decision-making behaves. So let me show you what that looks like. So a typical plot is something like this. PF, PD. Now you must remember that these two are plotted within a certain range, right? 0 to 1, 0 to 1. You put the phone on? Okay, these numbers are always plotted between 0 and 1 because they're probabilities. So typically when you plot PD of gamma versus PF of gamma, you're going to get some curve that looks like this. Okay? This curve here is called the receiver operating characteristic, or ROC curve. How many of you have heard of this ROC curve term before? Okay, it's a funny name to give to a curve like this, called receiver operating characteristic. It's an interesting history behind it. a lot of this theory and its applications were in fact developed during the early days of radar for World War II. And so what they did is they would build these big antennas, and they would look at the sky for signals. And then they would plot how often they detected the signal correctly versus how often they missed things, and they would get a curve like this. And so that was the performance of their receiver, of their radar receiver. So these curves then generically came to be known as receiver operating characteristics, or ROC curves. Now, there's a lot of interesting things in this space that one can draw. Let me, for example, consider this line here that connects 0 to 1. Straight line, 45-degree angle. This line is called the chance line. Why is it the chance line? Because along this curve, the probability of a false alarm and the probability of detection are exactly the same. Okay? What does that mean? It means that you're basically ignoring any data that you have, and you're essentially flipping a coin to make a decision. Right? So you get this curve called the chance line. Another reason why it's important to look at this chance line is because if you have designed a decision-making algorithm or system, then its performance must always be above this line. Right? Otherwise, you've wasted your time. Right? I mean, you should, if I give you data that contains information in it, you should be able to use that data to get a performance that is better than flipping a coin. Right? So, by the same logic, the farther away from this line your performance is, the better your system. So for instance, if your performance was here versus here, which system is better? The red one. Okay? So the farther away from this line you are, the better you're performing. Now, sometimes it happens that you get something that will do, something like this. Right, so the red and the blue will intersect each other, and what I meant to draw here, I don't know if you can see it, is that up here the red is slightly higher than the blue. Okay, so in this region the blue is better than the red because it's higher, but in this region the red is bigger than the blue. So then you have to question which one of these two is better. Well, it depends where you want to be on this curve. Okay, and that's something that's subject to more study that we will do as time goes on. But these kinds of curves are exceedingly important in engineering applications, and we'll see them again and again. All right, so let's do an example of what one of these curves looks like. So let's take our favorite example from earlier. So this is one Gaussian. This is another Gaussian. The mean here was 0. Remember, the mean here was 1. Okay? Now we set a threshold. Let's say, I think it was here. And this is gamma. Okay, we usually make a definition. We call the region to the right of gamma, we call this the critical region. Okay? Now with this definition, then let's write down the probability of false alarm and the probability of detection. Probability of false alarm is probability that x is bigger than gamma, given h0. Okay? This is the integral from gamma to infinity, 1 over the square root of 2 pi, e to the minus t squared over 2 dt. This is just the integral of a standard Gaussian random variable with mean 0, computed from gamma to infinity. And it's, of course, just this region here that we drew. Right? Okay, this integral, as you may or may not know, does not have a closed form. Okay, you can't compute the integral of e to the minus t squared in closed form. We have a definition for it. We call it the Q function. It's called the Gaussian right-tail probability. There's tables for it in MATLAB. You can find its value and so on, Q of gamma. Okay. On the other hand, PD, integral from gamma to infinity, of the other distribution. 1 over square root of 2 pi, e to the minus 1/2, t minus 1 squared dt. This is Q of gamma minus 1. So in MATLAB, the functions that will give you these are part of the statistics toolbox, and you can look them up. There's the inverse PDFs, there's the cumulative PDFs, and this is part of the cumulative PDFs. Okay, so CUM PDF. All right, so now we have these two functions, and we can plot them using MATLAB or any number of things. And what you will get is you will get a function that looks like this, depending on what value of what value of gamma you pick. All right, so while we're at it, let's make a quick observation. Since this is a false alarm and this is the PD, what would happen if gamma is set to minus infinity? Where would you end up on this curve for gamma equals minus infinity? Well, let's go to this one, right? Q of minus infinity. It would be the integral of minus infinity to infinity of this exponential, which would be 1, right? So PF would be 1. On the other hand, what would this be? It would also be 1, right? So what would happen is you would land at this point where gamma is minus infinity. What if you set what if you set gamma to infinity? Where would you end up? At the other end. You end up here. This is gamma infinity. In other words, this curve is parameterized by the values of gamma, right? As you step the values of gamma up or down, you move along this curve. Okay, and that's also a very important thing to know. Later on, you will see, we will come up with other criteria which will allow us to stay at one particular point on this curve. For instance, suppose that I wanted to minimize the probability of making a mistake overall. In other words, I took the type 1 probability and the type 2 probability, and I added them together. Okay? And I say, I want to minimize the sum of these two errors. What would be the best place to be on this curve in order to minimize that? I don't expect you to know the answer yet, but what you will see is that you will end up finding a very specific point on this curve that satisfies that condition. And it turns out, somehow magically, that point turns out to be a point on this curve where the slope is exactly 45 degrees. So it'll be a point like that. Okay? It turns out that point will be, on a line that's parallel to the chance line. So you kind of move the chance line up until you hit that curve at a tangent, and that point will be the point that minimizes the probability of error. Yeah?
Why that instead of, say, the point that's closest to, PF0 and PD1?
I'm sorry, say that again?
Why not? Why that kind of a point instead of a point that's closest to that upper left corner?
Well, those are different conditions, right? I mean, you can choose. Okay, let me make sure I understand your question correctly. Are you saying, are those 2 points the same? Right. In general, they won't be the same.
Yeah.
Right? So the point where the probability of error overall is minimized is not necessarily the same point as the one you described. Now what you're saying is, why should I pick the point where the probability of error is minimized? Well, you don't have to. You can have some other condition.
I mean, why is the probability of error defined as the point in the curve where you have a slope of 1 as compared to the point that's closest to the upper left corner of the graph?
Well, the problem is that you don't have a definition for what's the upper left-hand corner of the graph. Are you talking about this upper left-hand
Yeah.
corner, or are you talking about this? This.
PD equaled, I guess, the coordinate point 0, 1.
This point.
Yes.
Okay. So what you're saying is you want to find the point where you're closest to this guy.
Yes.
So you want to draw a line here on this curve and find that point.
More or less.
You can do that. But finding the optimum that way is much, much harder than finding the sum of the two error probabilities. Okay? So what you're saying here is, let's define this point and then draw a line perpendicular to this curve and pick a point. Well, draw a line to this curve and find the point on this curve that has the smallest distance to that corner. That's a different optimization criteria. You can solve that. I don't know off the top of my head what the solution would be, but you can do that too. Okay? Or you can say, I want to fix, right? I want to fix my false alarm rate at some number. Now find me the largest probability of detection. That's another optimization criteria. So you pick the right optimization criterion for your application and you optimize. What I just gave you is one example of how you can do it. Okay. All right, so everything that I described so far was done with a single data point. That, of course, even though it is interesting, it's not really the point of this class. The point of this class is to deal with many data points and try to make a decision. So let me summarize what we're going to do. What we have is we're going to gather data, and this is going to be some random process, x0, x1, xn minus 1. Okay? And then compute some function of the data. Let's call it t of x1, x2, xn minus 1. And then compare it to a threshold. If it exceeds the threshold, you declare h1 to be true. If it does not exceed the threshold, you declare h0 to be true. This is a definition or a notation that you may not have seen before. This. We get two inequality signs, one going one way, one going the other way. This means h1 is true, this means h0 is true. Okay, so going back to the example that I just gave you, this function was very simple in the example that I gave you. I didn't do anything to the data. I just took x and compared it to a threshold. But if you have a whole bunch of x's, now you can do lots of interesting things too. You can average these numbers together, you can square them and sum them together, you can take logs, anything. Okay? And then compare it to a threshold. This t is called a test statistic. And the whole question here throughout this class is going to be, what is the proper function t to use? Okay? How complicated should t be? Or for a given t, what's the performance of the detector? Or the decision-making algorithm? Okay, so the first step of doing this is, as I said, to assume that you don't have any prior preference for H1 or H0. And the result of that is you get something called the Neiman-Pearson. I'm going to set it up. I won't have time to prove it this time, but it's the so-called Neiman-Pearson test, or the Neiman-Pearson algorithm. What it does is it provides an algorithm which maximizes the probability of detection for a fixed probability of false alarm. Okay, this is very, very important because what it says is the following. You fix your false alarm rate. Let's say false, let's make it more real. Suppose false alarm, let's think about the fire warning system, right? Fire, if there's smoke or something, alarm goes off. But of course, it's extremely annoying if the alarm goes off every time somebody, burns a piece of toast, right? So the people that build these things, they have to decide how sensitive to make the fire alarms. When should they go off? So, somebody makes a decision. Somebody says, I want my probability of false alarm to be less than once every 100 days. In other words, if there's no fire, I don't want the fire alarm to go off. Not ever, because that's not practical, but it shouldn't go off more than maybe 3 times a year for no reason. Okay? So that's once every 100 days or so. So you fix that number. That number is given. Now you want to set your threshold. And you ask yourself, what should I set the threshold at so that I get the maximum probability of detection when in fact there is a fire? And it turns out the Neyman-Pearson theorem, there's a theorem, allows you to do that. Okay? For a fixed false alarm, what should I do to ensure that my detection probability is as large as possible? Now, this is an optimization criteria, and Neyman-Pearson shows us how to maximize it. Okay, so mechanically, this is how it works. So generally, you're given the data. Let's write it in a vector. L of x is x of 0 to x of n minus 1. From these, you compute a function L of x. This function is always a scalar. And you compare it to a threshold gamma. You get h1 or h0. Okay? But this L of x is nothing but t of x. There's a reason why I'm calling it L of x here. You'll see in a moment. So you take all of this data and you compute from it some scalar. So for example, it could be this. It could be x of 0 squared plus x1 squared, x of n minus 1 squared. And then you compare this to a gamma. Okay, now let's do a normalization too, just to be fair, okay? Because we don't want this to keep getting bigger and bigger. That's one example. Now if you take a look at this, if I were to replace these inequalities with an equal sign, what does this give you? Let's suppose just you have 2 terms, right? Let's say you have 2 data points, x0 and x1. And you replace this guy with an equal sign. What is that the equation of? This is the equation of a circle, right? Now if you put 3 terms, it becomes the equation of a sphere. If you keep n terms, it becomes the equation of an n-dimensional sphere, right? That's just an example. More generally, this function, L of x, equal to 0, or sorry, not equal to 0, equal to gamma. This defines a surface in the n-dimensional Euclidean space. Okay? And what happens is that basically this n-dimensional space is split into two pieces. Okay? One piece will correspond to the H1 hypothesis, and the other piece will correspond to the H0 hypothesis. So, you compute this function, and you look at this equation. This equation breaks the space into two pieces. Now, if you draw a data point, and you look at which piece of the space that data point falls into, that tells you which hypothesis you should pick. That's the idea. So, L of x bigger than gamma, this corresponds to H1. This is what we call the critical region. And L of x less than gamma, that corresponds to H0. Okay? And so what's PF? This is going to be the integral over R1. This is what I call R1. This is the critical region R1. Integral over R1, PDF of x given H0 dx, and PD is the integral over R1 again, P of x1, sorry, x given H1 dx. So what you do is you set this to some fix this at some number alpha, which you're happy with, like in the fire alarm case was 1 out of 100. And then this, what you want to do is you want to maximize this. And Neiman-Pearson tells you how to maximize this. Okay? So what you're doing is a kind of funny optimization. You're optimizing this region. Okay? Implicitly, by picking this function. This function implies the region, and that region implies the false alarm and detection. And Neiman-Pearson will tell you, as we will describe in the next lecture, how to pick this function so that you get the optimal splitting of the space into two pieces that will maximize the detection probability for a fixed false alarm. It's a very powerful paradigm for decision making. Okay? All right, I think we'll stop here, unless anybody has any questions. Questions? Okay. So please don't forget to turn in your homeworks, and don't forget that there's another homework due next week.